Okay, EC2 to K8S. I wanted to have a title that had only acronyms in it. EC2, of course, is AWS, and this describes the architecture that Stratastock uses today to supply hosted PBX. So, who am I? I'm the CTO of Stratastock. I'm also one of the co-founders. I've been doing this stuff for a long time. I'm an old Unix hack. And I've been doing telecom pretty much my entire career, all the way back to the 90s with dialogic cards, if any of you remember those. I built a whole voicemail system out of dialogic cards and was selling that in the early 90s. So I got into VoIP kind of in the 2000s and started this company, Stratastock, when I was living in the Virgin Islands. So half of our customers are actually down in the Caribbean, and the other half are up here. So when I came back to the States, we expanded and went nationwide, and we've gone through several re-architectures during this time. So I want to talk about our re-architecture this year, which happens to be based on Asterisk, and I know you guys are a free switch crowd, so please just globally search and replace Asterisk for free switch, and really my talk still makes sense. This is more about the platform than it is about how you're doing your voice.
All open source is welcome here, Jeff. All open source.
Yeah, we are completely 100% open source as well. So, whoop, what happened? Uh-oh. Oh, thank you. That's kind of far away too, but that's all right. So Asterisk, or free switch for that matter, is it actually scalable? When Asterisk came out, it was meant to be multi-tenant, where you can have different contexts and you can put different companies or customers in those contexts and they can have the same extension numbers and it really works. But at a point, like you can see in that graph on the side there, it seems to fall over. So if you're going to base a company and services off of something like Asterisk or free switch, you've got to find a way to be able to scale it. Now, we do have some people that have said they've got 1,000 simultaneous calls running through Asterisk on the appropriate hardware. I don't think it's a good design for us to try to do that. We wanted to find something that was maybe not requiring so much tuning, that just ran by itself, right, without all of that. So multi-tenant Asterisk. I decided pretty early on that we really didn't want to use context to do this, and that we wanted to run separate instances. The way to do this in the early 2000s was with containers. That was an idea that I had, and I brought it up in an IRC room in 2005, and basically was told that I was ridiculous, that Asterisk already does multi-tenant, and there's no reason to split it out. And basically, I was using a machine running LXC, to be able to do containers. So various different ways that we could try to break out doing individual instances for customers. Bare metal was actually how we started. We built small devices that we would put on site for customers, and that seemed to work okay, unless their power went out. And down in the Virgin Islands, of course, that happens a lot. Full VM, something like Proxmox or VMware, able to spin up VMs on your hardware. You get fairly good density out of that with a decent machine, maybe a dozen or so customers. And then containers. When we did some experiments with LXC, we found that we could get almost 100 customers on a reasonable box, and this was back in 2005. I've also known companies that have built their products on OpenVZ, which is also LXC-based. And that seemed to work really well back then. All of this requires orchestration of some kind. So it's fine that you can get your customers on containers, but how do you manage those containers? How do you route calls to those containers? Calls come into your head end. How do you know where they go? Redundancy. If your container dies, how do you get it restarted? And management, nightmare at scale, obviously. Bare metal, density of 1. So when we were building boxes and running Asterisk on them, it was just one Asterisk, one box. Hardware emulation versus kernel sharing is about containers versus doing a full VM. A full VM actually emulates the hardware underlying the machine, so you're wasting a lot of cycles, doing stuff that's not really necessary. Whereas containers share the host's kernel. And as long as you've got a host that is running the operating system you want your containers to run, that works really well. And for us, that was true. So we were an Ubuntu shop for most of our time with LXC. I think Ubuntu 12, actually. And we got, I want to say, up to 100 customers on a single Dell 710 back then. The hypervisor, one point for it back then was that the hypervisor has really good separation. So if you're going to build your service with VMs, you can be pretty well sure that one customer going crazy isn't going to kill the entire machine. With containers, that's not quite true. So we had a few instances where a customer's container ran some process that took over the machine, and that affected everybody. That's getting better, though. So C Group has gotten a lot better with their separation, and Docker is mainly the reason for that. So a lot of work has been done over the last 20 years to make that better, and now I don't have that fear anymore. We're able with C Groups to put limits on containers, and when I talk about Kubernetes, it's even more easy. Why waste cycles on idle PBXs in a VM? So instance orchestration. Orchestrating bare metal is hard. You can't spin up and spin down bare metal machines. And if they're offline, you kind of have to go on site to do something about them. So bare metal is really just hard. VM management, you can usually do with automation. There's APIs for Proxmox and for VMware. And it's pretty easy to write code to spin up and spin down customers' VMs. And then container orchestration options. So back in the early 2000s, you were pretty much limited to LXC, which is really low level. You basically make a directory with your container root file system in it, and it runs out of that cherooted directory. So it's pretty simple, but it gets the job done. Docker made that a little bit better. So Docker made an interface, a GUI. There's a lot of support behind Docker. And then Docker grew into Kubernetes. There's others. So there's commercial services for managing your containers. AWS has a service, I can't remember what it's called, but it allows you to spin up containers and manage them through the AWS GUI. Of course, they want to charge you for everything, so that's probably expensive. So this is our architecture as of today. I would say in 2018-19, we started designing, moving away from LXC and putting everything into the cloud. We were in data centers up to that point. I spun down 2 data centers and put everything into an AWS VPC. And now our customers get a full EC2 instance as their PBX. And each of those instances is orchestrated by our own internal interface. So we put a lot of blood, sweat, and tears into writing against their APIs and building kind of our own management GUI for this. And it works pretty well. We've been running this way for about 5 years. The only thing I don't like is that it's $15 a customer. And that doesn't sound like much. And truthfully, most of our customers are much more than that. A small office with, say, 5 or 10 phones is usually a couple $100 a month. So it hasn't been an issue until we start talking about how we're going to scale ourselves. So we want to do some national marketing this year and release our mobile app. So we have a SIP mobile app that runs on our infrastructure. And we think that that's going to have a lot of really small accounts. It's hard for me to sell a one-phone account today. The going rate for a seat is about $10 in my industry. So to sell a 1-seat account for $10 when it costs me $15 doesn't work. So we kind of recognize this and know that we need to get the cost per customer down. And we've decided that the way to do that is to go back to containers. Even though we spent all that time getting off of containers, we want to go back. So these are the goals of our architecture for this year. We want item-potent infrastructure. So it's really important to me that we have in a Git repo everything that's needed to rebuild our infrastructure from scratch. And that sounds crazy, but with Kubernetes, this is actually possible. You can have I'll show you later, but we can have a Git repo of Helm charts that just rebuilds everything from scratch. Eliminate single points of failure. We have a couple today, just the way that we've laid out EC2. Like we have our head end as a single point of failure. If it went down, it would affect all of our customers. And that bothers me. We also want to make sure it's across zones. Like AWS actually had an outage in US East this year, and it affected some really large companies. So I want to make sure that that whatever our design is, it incorporates if US East goes down, our customers still get their calls. I want to make sure we have better observability. That was all in-house written today, and to be honest, it's not great. So we were hoping to improve that. Improve security, another thing, we don't have really good separation. I won't tell you what the security issues are, but we know we have them. And I want to make sure we can scale to 100K simultaneous calls, which is really large. I doubt we'll get that big, but I want to make sure the design can handle it. And I really want to get my per customer cost down to about $3. So the final design turned out to be this. I don't know if you can see it, but there's kind of a cloud around this whole bottom area, which is meant to represent the Kubernetes cluster that we've built. The cluster spans 3 different AWS data centers. So there's one on the left here, which we're calling our primary. There's the secondary data center. Both of them are actually in US East, but they're 2 different data center zones. And then a third, also in US East, for quorum. The reason we need a third data center is for the database that's behind all of this. So Kubernetes manages all of your container orchestration in a database called etcd. And we have 3 nodes here, actually 5 nodes here called control plane nodes. These master nodes you see here and on the other side and the one in the middle. Those run the etcd database, and we have to have a quorum of these servers available. So more than half of the servers have to be up and running in order for the cluster to work. That's why there's an odd number. So with 5, you can kind of see it in your head. If you down one of the data centers, we have 3 left. No matter which one you take down, we have more than half left to be able to maintain redundancy for the database. So that maintains the redundancy part of our architecture. This kind of shows the path that a call would take from a carrier through, this would be an AWS Internet Gateway. So this is kind of the edge of AWS, and this is how the ingress comes in. So the call comes in to a customer pod, which I'm going to display in a minute, and then comes back out to the actual customer that has the extension that wants the call. The blue parts are encrypted in our infrastructure. Another thing that's interesting about our infrastructure is it's 100% OpenVPN. So all of our phones that connect, our app that connects, everything is OpenVPN and WireGuard. So I think this shows one going down, and the path just automatically flips over to the other. So this is actually functional today. So we could lose US East, one of the data centers in US East, and continue to function. We would lose the calls in progress, but people would be able to call back. I'm going to skip over this, but I thought with MLM, all these LLMs out there, we should put ChatGPT in the presentation somewhere. But I asked it to describe what Kubernetes does. And really, Kubernetes is managing your containers for you. So it's describing a structure of objects that allows you to keep track of customer pods that are running or having issues. It'll relocate them. It keeps the nodes balanced. It does all the hard parts for you of orchestration with just a little bit of code. So I'm going to apologize in advance. When I first found this clip, it was the real voices from these guys, like it was Kramer's voice. I guess they got in trouble because when I went to put the presentation together, this has been overdubbed, and it's the most horrible overdub you can imagine, but it's still pretty funny.
Figured out your infrastructure?
Yeah.
So what's your plan?
I decided to use Kubernetes. Massively distributed.
Just imagine their voices.
Whole new approach.
What are you doing?
Service mesh.
Service mesh.
Yeah, I'm getting rid of all my servers. All of them. And I'm going to build this multi-tiered service mesh. With APIs. And it will all be serverless. With all these containers. You know, like Kelsey Hightower demos.
You have a 3 team for this.
No, it's just me.
I don't see why you need Kubernetes.
The site needs to be 5.9 available.
Who's going to be maintaining it?
Oh, I don't need to.
And why is that?
It's in the cloud. There's a reason it's serverless.
Oh, for sure. You just need to write the code, orchestrate the containers, then configure Nginx, Kubler, Grafana, Datadog, and who knows what else.
Well, I already installed Docker, wrote my first container, and just need to sign up for AWS.
Hey, this is going to cost you thousands.
Don't you just need a Next.js site?
Yeah, well, this time you're wrong. I need global scale.
Seriously? You don't need global scale, you need a Raspberry Pi.
My visitors access the site in less than 2 milliseconds with JavaScript.
Your site is fruit jokes.
Anyway, there you go. So, K8's pods. This is what our EC2 container is going to become. So rather than giving a complete VM to a customer, they're going to get this structure. So a pod is a Kubernetes unit that represents a workload. And it's a collection of running containers. So these 3 circles you see in the middle, Asterisk, Nginx, and TCP dump, are containers that have been collected into what we're calling a customer pod. These live on a virtual network that is pod specific. So these containers all talk to each other on the loopback interface. They expose ports to be able to produce services. So this particular pod is going to expose the SIP port, obviously, and TCP port 80 for a web interface that we're designing for our customers. So that Nginx pod is really just going to be running the customer interface, and the Asterisk pod obviously just runs Asterisk. That's kind of the Kubernetes and the Docker way, is to split services out into containers, right? So the redundancy. The dark words are Kubernetes concepts. So deployments are a concept of defined state. When you have a workload, you want to specify things like how many min and max of these pods do you want to live? How do you want them to start again if they die? Where are their logs going to go? All of these things can be defined in the deployment. Replicas are inside the deployment. It's how many of the pods you want to run. Daemon sets launch on your nodes. So when you make a Kubernetes cluster, you're really using machines or VMs that represent nodes in your cluster. And a daemon set runs a pod on every node in the cluster. This would be for stuff like network control or storage. Those would be reasons to have something running on every node. Node failures cause pods to bounce. That just means that they're shut down and they're started somewhere else. Now, the way a pod is designed, it shouldn't matter if it dies and starts somewhere else. There should be replicas that are handling the load while it goes down and comes back up. So if you've designed your workload correctly, then bouncing really has no effect on your service. Individual replica failures don't interrupt service. That's what that means. And then the etcd database I talked about already. So as far as my goal of redundancy, I think this fits the bill. It has all the pieces that I need to put together a redundant architecture. Security was another thing that I was concerned about. In our EC2 world, things are fairly wide open inside our VPC, kind of the soft, chewy center. With Kubernetes, it doesn't have to be that way. You can overwhelmingly granularly specify security. We're probably not going to go super deep, but we can use namespaces to achieve the separation that we're really looking for. So we have kind of a rich reseller setup where we've got lots of people selling our services. They're going to get their own namespaces in our cluster, and they'll only be able to see the pods that they're selling for us, for example. Networking is still generally pretty open. We have the tools we need to make that tighter, and I may try to do that, but it's not really one of our prime goals this year. And then cluster scanning. If you go to any of these Kubernetes conferences, half the floor is security people. They want to scan your containers, they want to scan your cluster, and it's really, really hard to set up a cluster securely, so I can see why this is big business. So in order to make this work, I've got to get Asterisk or FreeSwitch installed in a container. So I've got to Dockerize it. I didn't start from scratch. There's a great GitHub mlan Docker Asterisk. And I spoke to the guy, made sure he was okay with me mentioning him, but you should check out his repo. It's really a great start if you want to run Asterisk. There's a couple of things that make a containerized version of either of these, Asterisk or FreeSwitch, difficult. Things like logs will blow out ephemeral storage in your cluster. So you don't want a container that's going to run pretty much continuously writing to the local host disk. So you've got to make sure all of your logging is going by a syslog or somehow getting out of the container and not starting to fill the disk. And then a startup script, really, that configures it at launch. Deciding whether we're going to be on-prem or cloud. So we had some discussions about actually going back to data centers. In my daytime job, I manage a bunch of Kubernetes bare metal clusters for fintech operation in Chicago here. So I know how hard it is to set up a data center in bare metal, and I still talked about it, but we have decided to stick with Amazon. So we're going to run our cluster on EC2 instances. And each instance will be a node. Now, Amazon and Google and probably other cloud providers have their own Kubernetes services that they offer. So if you really want to make it easy, Amazon's EKS is simple. With a couple of CLI commands, you've spun up a cluster and you can start playing with it. I'm sure Google's the same, although I haven't tried it. It's expensive, though. So you don't get much for an EC2 instance. An 8-core 2x large is $200 a month, and in order to have a reasonable cluster, you're probably looking at 10 nodes. So it's really quite expensive. On the other hand, if we went back to data center employees that are Kubernetes aware, they're extremely expensive. So I think that's really what did it for us. We're going to stick with the cloud. YAML is the kind of the language of Kubernetes. These YAML objects are how every object in the cluster is defined. So this is what I was mentioning earlier. If you set up your cluster with what's called manifests, which are collections of these YAML files, you can imagine having your entire infrastructure defined in these YAML files in a Git repo, and you can rebuild your cluster and all of its applications anytime you want. That's pretty powerful. So we've taken that and used YAML to describe our customers. So this is probably hard to read, but the idea is that we can use YAML to spec PBX. So the PBX is kind of the top level. The PBX contains extensions, it contains IVRs, it contains ring groups. Each of those can be described in YAML for a customer. So for every customer, I've got just a YAML manifest that I can rebuild their PBX at any time as well. In fact, the way this is set up, making a change to this is stored in the database, the etcd database, and I can pull it up with a command and edit it. And when I put it back in the database, if anything's changed, that change actually happens in the cluster. So that's actually very powerful as well. I wanted to touch briefly on the components that we've chosen. So if you're setting up a Kubernetes cluster, you've got lots of choices. There's a foundation called the CNCF that is kind of managing all of these projects. If you want to write a Kubernetes application and get it in front of the CNCF, you'll have a lot of people that'll see it that way. So all of these different components are CNCF projects, and we've decided to use them for various reasons. So cluster management is about spinning up the cluster, managing the state of the cluster, having that idempotent infrastructure, being able to use a Git repo to rebuild it. For that, we've decided to use kops. There's a reference at the end. You can check out kops. But there's lots of other options. KubeSpray is one that I've used before. EKS, of course, from Amazon, or GKE from Google do this for you as well. Persistent storage. You can imagine if you've got a cluster of 15 nodes and your customer pod spins up on one randomly, it's going to have access to its voicemail storage and other things that you might want to store with the PBX. That requires something that will connect to your workload with the storage wherever it happens to be. So we've decided to use Rancher Longhorn for that. Rancher is kind of cool because it makes each node a storage node. So you put aside some local disk on each node. For us, that's EBS volumes. And the Longhorn manager, which is in the cluster, you tell the Longhorn manager, I want 5 gig of space, and I'm going to name it this. And it just finds a place to put it and replicas for it. And usually by default, I think it's 3 replicas. So it's kind of spread throughout the cluster. You've got your data. And no matter where your pod spins up, you end up with an NFS mount to it. And that all works really well. Networking is another big deal. Pods need to be able to talk to other pods. They need to be able to discover services and connect to them. And they need to be able to get in and out of the cluster. So all of that requires some fancy networking. There's a lot of different options here. Cilium is kind of cutting edge. It uses eBPF to do all the routing in the kernel. So none of the packet routing enters user space. So it's super, super fast. We've decided to use that. Control plane database is etcd, but you don't, that's by default, but you have other options. For us, the Kubernetes environment on etcd just was the default, so we used that. Ingress integration, so how you get, if you've got 500 customer pods and one IP address that all the web requests are coming into, you have to have something that sends it to the right place. And for that, we're using traffic. Again, there's a million different options. Nginx is another really popular. It's basically a reverse proxy that works with Kubernetes. And then VPN ingress. So we, as I mentioned, run OpenVPN at our front end, and everything has to go through it to get access to the customer pods. And we're doing that with Nginx as a reverse proxy. And finally, observability, which was another of my goals. Prometheus is really the de facto standard for Kubernetes. It has support for lots of things plugging into it and then lots of things consuming from it. So we decided to go with Prometheus, and Grafana is how we graph things and look at things. And finally, Homer is our SIP call analysis software. And all of this is actually functional at this point. So the last thing that I had for, I've only got just a few minutes, so I'll skip over a lot of these, but the last thing that I had for a goal was 100,000 simultaneous calls. So back in January, I did this talk at AstraCon, and we had just finished this experiment. So I'll just briefly talk about it. We set up this on AWS. We used EKS to quickly set up the cluster. And we set it up so that each of these nodes would run a configurable number of customer pods. And the customer pods were configured to just make a call to the call router, which was another pod. This is a daemon set, actually, right? Runs on each node. It makes a call that gets routed back to itself. And I was able to control how many of these I was running, so we did this test to see just how many we could get. That explains how the test works. This is a quick TCP dump. If you want to take a picture, this tells you the RTCP information, loss, and jitter. So we were collecting that as we ran the test. And I did want to try to play this really quick. This is what, when it was working well, it sounded like this.
Congratulations.
You can hear them talking over each other, right, in both directions. But they sound good. All right, that's enough. So with 100 simultaneous calls on one node, you just start to see jitter start to happen. And we thought that was interesting. Then we went to 5,000 customers, 10,000 simultaneous calls on 100 nodes. And this ran for about an hour while I did some tuning in the background. And it's kind of hard to see here, but we tuned it a little bit. This is what bad audio looks like. You know, nothing like the other graph. I don't have the audio of this, though. And then finally, packet loss and jitter we sent to CloudWatch, another AWS service, so that I could do this graph. So this was the giant test and the crappy audio. This is latency. So you can see the audio is really crappy right here. We did some tuning and we got it down to this. So this is literally 10,000 simultaneous calls with audio that sounded like you heard before. So I felt pretty confident that that we could reach our 100,000 by having basically 1,000 nodes running, which we know we can do on Amazon. So that's all my goals satisfied. I'm pretty happy with the design. This is our front end GUI. And this is how we edit things into our database, and then Kubernetes takes it from there. A couple tuning thoughts. We had to tune it a little bit, right, to get past that audio issue. And it was really about how many pods we run per node. And we figured out the right ratio, so we feel good about that. We also think that we'll probably, when we go to scale, go on Metal at AWS rather than using VMs. Conclusions. Horizontally scaling obviously works. We kind of proved it. We maxed out a node group with 100 nodes. So we think we can do the 100K simultaneous calls with 1,000 nodes. And we can do that with 10 node groups. Density of customers allows us to get to $3 per customer. I think we got to like 260 or something like that. And then we plan to finish this by the end of the year. And I got some references. These are basically the components that I talked about. And that's it. I have 30 seconds for questions, maybe.
Well, Jeff, in the interest of keeping things on time, I'm going to ask people to come and see you with their questions at lunchtime, if that's okay. But let's give Jeff a big thank you.